Okay, today we're going to talk about the viability of a solution. So it depends on the problem how you can tell if something's viable or not. So we'll look at a couple examples. The first example is, let's just look at a good old-fashioned two-step equation. 2x plus 5 is equal to 7. And we want to know if the solution is viable. So let's say that I'm telling you that x is equal to 3. Well, to be viable means that it is a correct solution. Means that it's accurate. So from an equation, you could simply plug it in. So we could check it. So we put 3, and instead of x, we're going to replace, should be 2. And instead of x, we're going to replace 3 plus 5. And we want to find out if this is indeed equal to 7. So 3 times 2 is 6. 6 plus 5 is equal to 11, which is not 7. So this solution is not viable. And you can do that with any solution. So we used to call this check your solution, and it still means the same thing. So anytime you have a solution, you can check to see if it's viable or not by seeing if it's true in the original equation. And that is true no matter what this equation looks like. It's also true for systems. It's true for inequalities. But viability can mean more than just check your solution and see if it works. So for instance, let's look at a system of equations. And we might figure out a pair of numbers that work in this system right here. So say we got 2 times 1 plus 8, and that is 10. So we could say that the solution 1, 8 is a solution here when x is 1 and y is 10. But that doesn't mean it's a viability for this solution because it has to be true in both. It is true in the top, but let's see if it happens to be true in the bottom. And since I just randomly picked those numbers, this would be astonishing if it is. And 3 times 1 is 3. 5 times 8 is 40. And when we subtract that, we definitely do not get 6. So this is not a viable solution for the system, even though it was viable for this top equation. So when you're looking at systems, the viability must be true for both of them. So what if we were graphing these? Because a lot of times when we look at these, we look at graphs. So let's say that I have a nice, beautiful coordinate plane, and I'm using, say, this line. Well, where are the solutions? The solutions are any point that happens to be on the line. So if I ask about that point right there, the screen point, that's a solution. If I ask about this point, that's a solution. If I ask about this point, that's a solution. Conversely, any point not on a line, say that point, is not a solution. So what it means to be a solution is that it is on your line. And then when we look at intersecting lines, which is what the systems are, we are looking for where the two lines meet. This is the solution because these are all the solutions for the red line. These are all the solutions for the green line. This is the only solution to both lines. So you can always look at that. And then, of course, you have a couple interesting cases. One is that these lines end up being exactly the same. So if you have two lines that are right on top of each other, that means every single point work, and we call this all real numbers. The other thing that could happen sometimes is that you have, say, parallel lines. And these solutions, these two lines would never intersect, so this would mean no solution. So this would be a graphical way to look at the same types of problems instead of just plugging numbers in and checking. But there's even more that's involved with a viability of solution, and that is real life. So say that I'm doing a problem, and I'm looking at a line, and it says that these are all my solutions. Okay, and maybe we're talking about height here of a person. They're jumping, and this is the time that it's taken. So as time goes on, their height continues to fall. And this would make sense because as I jump, I go down. So time would increase as my height goes down. But what happens right here? So this is the point when I'm on the floor or I'm on the ground. Can I continue to go beyond the ground? So I hope your answer is no, that the ground would stop you. So even though this line continues to go, this part of the line is not viable. Because the problem itself that I gave you, that I'm jumping off from somewhere and I'm falling, this part of the line doesn't exist. So we call this part not viable. So it has to be two parts. One, it has to be on your line or a solution when you plug it in, but it also has to make sense in terms of the context of the problem. So anything below the ground doesn't make sense, as well as this section up here. This section up here is before I jump. Now, according to our line, it's saying that I was continuing high and I was dropping forever when I jumped off a cliff. But in reality, I probably just started here. So what really is happening, if I looked at real life, is I was probably just standing on the cliff for a while, not changing my height. Then we jumped off, and we're not going to kill ourselves. So this is like a small cliff where you're jumping into the water or something. So think of more like a swimming pool. You're jumping off the diving board. You fall, but then when I get to the pool, you know, maybe I go down just a little bit, and then I'm going to sit here and I settle right here on the surface. We don't go down forever. So this would be real life what happens, even though our math equation says that it both continues in the negative direction forever and the positive direction forever. We're only valid in this section right here for our equation. So this has to be in terms of context of the problem. So when you read a story problem, make sure it makes sense which part of the answer it is, and look for things that don't make sense. For example, going below ground when you shouldn't be doing that, or things that happen before time starts. If you have other questions, make sure you ask. But this is a really important thing for the SAT. They will ask you questions like this where it's going to find out whether or not you realize that this doesn't make any sense in terms of real life.